GMAT all day.
This final ratio question, I have called it a combined ratio question. That just means it combines all of the different types of ratio questions and all the concepts we have learned in the previous video, which means this should be the most complicated video in the series. But the thing to look out for is how the way I approach it really is not all that much different than the way I approached that first simple video. So when I see a question like this, I am not thinking to myself, oh no, a hard ratio question. I am only thinking, yes, a ratio question, because all ratio questions are pretty much the same to me. So this says, Ronald has a bag containing green, orange, and yellow jelly beans, such that the green to orange ratio is 4:3, and the orange to yellow ratio is 2:1. Nancy has a bag with green and yellow jelly beans, and a ratio of 2:5. Together, Ronald and Nancy have 26 yellow jelly beans. How many green jelly beans could Ronald have? So that stands out to me as something a little bit different about this question that hasn't been asked in the previous ones. They're asking what could be true here, whereas opposed to the other ones where we were basically asked to solve for a single value. So this is sort of implying there are going to be multiple values that Ronald could have for his green jelly beans. So we have to find a property that is common to all of them to figure out which of these choices could be the answer. So let's go back and start setting up our ratios. So Ronald has a single bag with 3 types of jelly beans in them. And they give us 2 different ratios though. So Ronald has green to orange. As 4:3. So we'll say 4x to 3x. And then he also has orange to yellow. In a ratio of 2:1. Here we gotta call that 2y, y, because we have separate ratios. Then we have Nancy, who is a little bit simpler. She just has a single ratio of green to yellow. In a ratio of 2:5. So this is a third ratio, so we'll call this 2z, 5z. So this is our ratio set up. Then they say together, Ronald and Nancy have 26 yellow jelly beans. So that is y plus 5z is equal to 26. And then we need how many green jelly beans Ronald could have, which means what could be the value of 4x. So they give us information about y and z, and then they ask us something about x. So what should we do here? So I would say first, we really did not fully set up our ratio here, because for Ronald, we could get this in terms of a single ratio of 3 things, because our ratios are connected through his oranges. So let's do that. Then hopefully we can connect x to y and z somehow. So my single ratio is just going to be my greens to my oranges to my yellows in Ronald's bag. So green to orange, 4x to 3x. Orange to yellow, 2y to y. And that means 2x, just say 3x, must be equal to 2y. Because the oranges are the same, regardless of whether they're being compared to the greens or the yellows. This is all I know. Let's get everything in terms of, I think in the last video, last time we had to do this, we got everything in terms of y. Let's get everything in terms of x. This one. So that means if we want to get everything in terms of x, we got to put this equation here in terms of y. So y is equal to 3/2 x. So if we want to get everything in terms of x, we want to get all of Ronald's jelly beans in terms of x. We can keep his greens the same, because those are already in terms of x. That stays as 4x. For our oranges, we want to get everything in terms of x. We can choose between x and y with orange, so we want to choose the 3x. And then for our yellows are what we have to change. And so we know our yellows are equal to y. That's a coincidence. And we know y is equal to 3 halves x. So our yellows are really just saying y, we'll say 3 halves x. And if I want to get all my coefficients as integers, I got to multiply everything by 2. And if I do that, I get my greens, 8x green jelly beans, 6x orange jelly beans, 3x yellow jelly beans in Ronald's. Back. So what I might do now is finish setting this up, put this onto a page. This is Ronald's bag. Sorry, it's green to orange to yellow. Then we got to bring in Nancy. Green to yellow, 2z to 5z. So this is Ronald. Then Nancy. To the to 5z. Together, Ronald and Nancy have 26 yellow jelly beans. So now that everything here is in terms of x, we can write that as, because before here, we still had in terms of y over here. Now that everything's in terms of x, we can say 3x plus 5z is equal to 26. Okay, so what does this mean? Can we do anything else? Can we get our z in terms of x as well, and we'd be able to solve for x, which I don't think we would be able to do. Otherwise, they wouldn't ask us how many green jelly beans could he have. So I think that's really as far as we can go. So before, they're asking us about something about x, right? Because they're asking for what could 4x be? Ronald's green jelly bean. But they only gave us this one equation that didn't tell us anything about x. It only told us about y and z. So all we were able to do is we were able to find a way to introduce x into this equation, replace our y with a 3x. And so this should be, I don't think we can do anything else. So this should be enough to get to our answer. So they're asking which of the following could be true. So what could Ronald's green jelly beans be equal to? So we changed, we had 4x before, then we multiplied everything by 2. And so we're looking for what could 8x be? It still comes down to, well, what could x be? And so let's think about this for a second. We know 3x plus 5z. And so 3x, that is the amount of the number of yellow jelly beans that Ronald has. 5z is the number of yellow jelly beans that Nancy has. So 3x and 5z each have to be integers. They got to be whole numbers. You cannot, we're assuming that we don't have any partial jelly beans here. So given that, I think it's safe to say that this means we have some multiple of 3 plus some multiple of 5, which is equal to 26. And so if you think about it, if x and z could be anything, well, there's infinite possibilities here. But the fact that we have to have whole jelly beans actually means we are very limited in the numbers that we can have. Because, for example, if we start just plugging in values for what could x be, so could x be equal to 1, for example, then we would have 3 here, and we would have to have 23 over here. So x is equal to 1, this is equal to 3, means this has to be equal to 23. This can't be true because this has to be a multiple of 5, which 23 is not. So this isn't possible. So what about x? X is equal to 2, 3x is equal to 6, means this here has to be equal to 20, which means that works when z is equal to 4. That is true. So this is possible. X could be equal to 2. If x were equal to 2, remember we're looking for 8x. 8x would be equal to 16. That is not an answer choice. So I'm thinking either we did something wrong or we got to keep going. but this works. This could have been an answer choice. X is equal to 3. So when X is equal to 3, this is equal to 9. What plus 9 is equal to 26, 17. So 5z would have to be equal to 17. That can't be true because that's not a multiple of 5. This is out. X is equal to 4. 3x is equal to 12. This, therefore, has to be equal to 14. That cannot be. 14 is not a multiple of 5. X is equal to 5. Got 15 and 12. That's not possible. 12 is not a multiple of 5. X is equal to 6. You see where we only have a finite number of options because once this is over 26, but we can stop. Right now we're at X is 18. We can sort of quickly. This is our last possibility because after this, 3x would be equal to 27, which is over our total number of jelly beans. So this is 18. This here must be 8. That's not possible. 8 is not a multiple of 5. X is equal to 7. 21. This is 5. So this works when z is equal to 1. 5z is equal to 5. And I'm guessing this guy here will not work. 5z cannot be equal to 3. So when x is equal to 7, that means Ronald has 21 yellow jelly beans, 3 times 7, and Nancy has 5z, which is, we said z was equal to 1 in this case. So 21 plus 5, 26. That works. So remember, we're looking for 8x, Ronald's green jelly beans. So x is equal to 7. 8 times 7 is 56.